All right, where we left off in class was we were talking about electron configurations. Quick recap. We started with hydrogen. We said that's a 1s orbital, 1 electron, so it's 1s1, whoops, 1s1, 1 electron. Helium, there's 2 electrons, it fills the s orbital, that's 1s2. Lithium is the next atom, that fills the 1s, and it also fills the 2s, so 1s2, 2s1, 1, 2, 3 electrons. Beryllium, 1, 2, 3, 4, 1s2, 2s2. Okay, remember we did this in class for all these. Now we start getting into the p orbitals. There's 3 p orbitals, so it's 1, 2, 3, 4, 5. 1s2, 2s2, 2p1. Remember back here in hydrogen, we wondered, should this be up and down, or should they both be up or down? Remember we had this thing called the Pauli exclusion principle? That says no 2 electrons can have the exact same configuration. That means you can't have 2 electrons in the same box pointing in the same direction. They have to pair opposite to one another. Carbon, the reason why I bring this up is the next one we had to wonder about was carbon, and we found out that that one does something like this. It puts 2 electrons spinning in the same direction but in different boxes. This is called Hund's rule. And Hund's rule basically says, all right, electrons are in a suborbital are going to line into different boxes, and they're going to be spin parallel to one another. Nitrogen, my drawings are getting sloppier and sloppier. 1s2, 2s2, 2p3. Oxygen, 2p4, which looks like this, 1, 2, 3, 4. You might be asking yourself, do you have to draw it over in the left box? No, you don't. You can put it in any of these boxes, but you do start spin pairing it opposite. Fluorine, I'm getting lazy here, just writing the p orbitals, 1, 2, 3, 4, 5, and then neon, one, 2, 3, 4, 5, 6, 2p6, 2p5. Okay, now you also might remember we talked about diamagnetic and paramagnetic. If all the electrons are paired, like they are here, we call that diamagnetic. This guy is also diamagnetic. This guy is also diamagnetic. Okay? So if you're looking on the periodic table, I just said helium's diamagnetic, I just said neon is diamagnetic, I just said beryllium is diamagnetic. All the rest are paramagnetic. So where do the diamagnetic ones show up? Where do the paramagnetic ones show up? Whenever we have a block of elements getting filled, whenever we have a suborbital completely getting filled, that's diamagnetic. Haven't quite talked about this yet, but might as well here. These are the d orbitals in the middle, the transition metals. These are all p orbitals. These are s orbitals. And these are f orbitals that are being filled. Okay, so whenever a complete block gets filled, those are diamagnetic. All the other elements on the table, or on the periodic table, are paramagnetic. Most of them are paramagnetic. Okay. So we've gone 1 through 10, no problem. You're not going to want to sit through me doing the rest of the periodic table, the other 100-some elements. So let's give us some ways to figure out the rest of the elements without having to watch me do all these. Okay, and what I'm going to do is I'm going to give you some principles or rules to follow. First thing I'm going to tell you is the transition metals are the ones, as always, the bad boys, who break some of the rules. And let's try to understand first the filling order. You've just taken my word for it, but let's take Let's take a look at the energy filling diagrams.